Today I'd like to introduce you to series and parallel circuits. Most of our attention today will be on series circuits, but I want to introduce you to both. So, this is a series circuit. A series circuit has one path for the electrons to follow from the time they leave the battery to the time that they return. So in this instance, the electrons would come out of the negative, they would flow through the first light bulb, the second light bulb, all the wire, third light bulb, back to the battery. That is known as series, one path. Now you'll notice all three bulbs are on, but if I unscrew one bulb, all three of them shut off. A series circuit has one path, so if I break that path by a switch, by a fuse, by a circuit breaker, or by removing one of the lights, having one of the lights break, they all go off. Series circuit, a break anywhere shuts down the entire path, shuts down all the objects on that path. The second type of circuit is known as a parallel circuit. With a parallel circuit, there are multiple paths. So the electrons would flow through this wire, and when they get to this junction, some of them will take the top path, some will take the middle path, and some will take the bottom path. Each path is independent of all the others. So a parallel circuit, there are multiple paths. And if we take one of the bulbs out, the other two bulbs continue to glow. Every path is independent of all the other paths. Parallel circuits. Let's focus today on series circuits. So like I said before, in a series circuit, there's only one path. If you want to have a switch control your bulbs, you want the switch in series with the thing you're trying to control. So here I have three different switches. This is total overkill. But if I turn off any of these switches, the light bulb is going to go off. It doesn't matter if the switch is before the lights, in between the lights, or at the end of the lights. A break in that circuit shuts down the flow of electricity in all parts of the circuit. Okay, so here's our first real series circuit. This is a series circuit with a resistor and a speaker. So, what I'd like you to notice is the speaker itself has a resistance of 8 ohms. That's the coil of wires inside the speaker. Later in the year, we'll learn how speakers work, but for now, it's 8 ohms. Connected in series with that is a resistor that is orange, black, silver. We're going to ignore the silver. We're going to assume the resistor is perfect. And we're going to say that resistor has 33 ohms worth of resistance. Orange, black. Okay, 33 ohms. They are connected in series. If it wasn't connected in series, this resistor wouldn't be doing anything. All right, so the way we draw it out is like this. We're going to power our speaker with a 6-volt source. Okay, we're going to send that voltage to this speaker and resistor, and they're connected in series, so we draw them like this. This symbol is the symbol people sometimes use to indicate a resistor. So we have a real resistor and then a resistor that actually is the speaker itself. Okay, so this can be a stand-in for anything. A light, a speaker, a fan, a motor, doesn't matter. Okay, so how do we deal with this? Well, since there is only one path for the electrons to follow, that means the electrons are going to have to go through both items, the resistor and the speaker. So we start by adding together the two resistances, and we get 41 ohms. Okay? Series circuits. Add the resistors together. The electricity must go through both. Once you have the total resistance, you find the current by using the formula current equals voltage divided by resistance. The voltage is 6, the resistance is 41. So go ahead and work that out. That will give you the current that is coming out of the battery. And again, this is the symbol we use for a battery. Negative end is the small, positive end is the longer one. So we get our current, and since there is only one path for the electrons to follow, we can find the voltage for each component by using our main equation again and again. So use the current that you got here along with the 33. That'll get you the voltage here. Use the same formula again at the 8 and find your voltage there. Okay, I did this earlier. I got a current of about 146 milliamps. I use that current along with 33 for my resistance, and I get a voltage there of 4.83. And I use it at the speaker itself, and I get 1.17 volts. Okay, at that point, I might want to find out how much power I'm getting at the speaker itself. So power equals VI. I have the V and I have the I. Remember, every component gets the same current because there's only one path. This comes out to a power of about 0.17 watts. You'll notice that this speaker is not supposed to go much above 0.1 watts. Well, we're a little bit above. I don't think we're going to be in much trouble. We might want to drive this with a smaller amplifier. We may want to have the voltage maybe down around 3 volts instead of 6 volts. Okay? But I still think we're going to be okay at 6 volts. We're not that far above the recommended max power. However, if this resistor were not here, we would have gotten a lot more current, and then we would have gotten a lot more voltage at that part of the speaker, and we would have gotten way too much power, and we would have blown out the speaker. So again, the purpose of this resistor is to keep the power getting to the speaker at a more modest rate. It lowers the current, it lowers the power. Okay, I want to try it with a hair dryer. Okay, so with the hair dryer, we have the heating elements inside the hair dryer. We have the long cord for the hair dryer, and we want to see how much of the energy gets used up in the cord. We don't want any energy to get used up in the cord, but that's not realistic. So what we're going to have to do is break this up into 2 separate things. The power cord and then the heating element inside the hair dryer. So the cord itself is 18 gauge aluminum wire of 1.5 meters. So use that to figure out the resistance of this wire. I'll give you a moment to do that. Remember how to deal with gauges, and remember how to look up your resistivity. Okay, when all is said and done, you should get a resistance of 0.0513 ohms. And you think, wow, that's a low resistance. Why am I even worried about it? Well, let's hold that off to the side for a little bit and see if it becomes important later on. Next, we want to do the heating element itself. That's the heating element inside. It's 28 gauge nichrome, 60 centimeters. So try to work your way through that so you remember how to use this formula. You want to get good at this. You want to be able to do it quickly. So look up your value for nichrome. Make sure you turn your centimeters into meters. And make sure you're working with 28 gauge wire. Okay, so you have all this stuff. We've gone through this before. When all's said and done, you should get a resistance of around 8.15. I had mentioned before that we use nichrome when we want to have a relatively high resistance. As in terms of resistance, this might not really be that high, but it's high compared to the aluminum wire that brings the electricity to the heating element. Why is that important? Well, let's now look at our circuit. We're using 120 volts because we're hooking it up to an American outlet. We're going to represent the the aluminum wire, the power cord, as a resistor with 0.0153 ohms. Then we have the heating element, that's this one here, 8.155. And then we have another wire. Even though it looks like just one wire, these are actually two wires that are joined together to carry the electricity back to the outlet. So we have two aluminum wires, one nichrome wire. How do we deal with this? We add all the resistors together because the electrons have to go through the cord, through the heating element, and back through the cord again. Okay, when we add them all up, we get a total resistance of 8.26. Somewhere in that ballpark. You might round it to more decimal places. I wouldn't go any less than this. Okay, once you have that, that is your total resistance. Use your formula, current equals voltage over resistance for the total volts and the total resistance. That'll get you your total current. When I did this, I got 14.513 amps. Oh, let me fix that. 513 amps. Okay, 14.531 amps. That current is going to go through the aluminum cord, the heating element, and the cord again. And when you figure out the voltages, you're going to get a voltage of 0.746 volts, 0.746 volts, and about 118.5 volts. What does all this mean? It means we thought we were getting 120 volts to our heating element, but inside this cord, we lost almost a volt and a half. So what? Well, that volt and a half generates power inside that cord. We don't want power inside that cord, but we're getting a little bit of power. So we do power equals VI. For the voltage, we're going to add the two voltages together of the cord. That is like 1.49-ish, something like that, times our current, which is 14.531. And we get a power lost inside the cord of almost 22 watts. So who cares? The reason why we care isn't because it's going to take a little longer to dry our hair. It's because that power is going to generate heat. And if we generate too much heat in our power cord, it can be a potential fire hazard. So the important thing to realize is when you set things up, you want this cord to have the smallest possible resistance. This one we want to have a larger resistance. This one should be large enough that we don't blow a fuse. This one should be small enough that we don't lose a lot of power inside that cord. Series circuits. They're very important because most things involve multiple components connected together. I have one more I'd like you to try on your own. 6-volt battery hooked up to 3 resistors. I want to see if you can find the total resistance, the total current, the current going into each one, the voltage of each one, and finally the power of each one.